Welcome to urban mining, where 1 ton of electronic waste contains 800 times more gold than natural ore.
In 2022, the world generated 62 million tons of e-waste, worth $91 billion in precious metals.
Only 20% gets formally recycled.
Modern facilities process 50 tons daily, recovering precious metals worth 3 times the processing cost. Initial screening removes hazardous components requiring special handling, like batteries and toxic displays. Gold-rich components segregate for maximum recovery. CPUs contain 0.2 grams, motherboards 0.3 grams per kilogram. Trained technicians systematically dismantle devices, preserving intact circuit boards for chemical processing. Circuit boards use gold for corrosion resistance. Connectors, pins, and traces contain recoverable precious metal. Computer processors average 0.2 grams gold each. 50,000 CPUs yield 1 kilogram worth $67,000. Each smartphone contains 0.034 grams gold in circuits. 6 million phones produce Tokyo's 5,000 Olympic medals. Automated conveyors route materials by gold density, high grade to leaching, low grade to smelting. Component storage maintains inventory tracking, ensuring batch traceability throughout extraction process. XRF analysis verifies gold concentration averaging 200 parts per million in circuit boards. Pre-processing strips plastics and aluminum, reducing material volume by 60% before leaching. Eddy current technology separates non-ferrous metals, aluminum and copper route to dedicated recycling streams.
High-torque shredders grind boards to 10 mm particles, increasing surface area for chemical extraction. Chemical leaching dissolves gold from shredded e-waste, using modern cyanide-free alternatives. Breakthrough 2025 method uses pool disinfectant activated by saltwater, achieving 98.2% gold extraction.
Gold oxidizes and dissolves at room temperature, eliminating energy-intensive heating, reducing processing costs.
Komagai bacteria concentrate gold 1,000-fold within cells, requiring only heat and drying for recovery.
Older methods use nitric and hydrochloric acids, requiring temperature control and extensive safety measures.
Controlled leaching maintains 25 degrees Celsius, optimizing gold dissolution without damaging other valuable metals.
After 6 hours, solution contains 200 milligrams gold per liter ready for precipitation.
Multi-stage filtration removes undissolved solids, leaving clear gold-bearing solution for recovery. Residue analysis ensures extraction efficiency exceeds 98%, minimizing precious metal loss.
Gold solution advances to precipitation, where chemical reduction converts dissolved gold to solid particles.
Sodium metabisulfite reduces gold ions, causing pure metal to precipitate as brown powder. Gold particles coalesce and settle over 2 hours, forming concentrated slurry for filtering. Vacuum filters capture gold powder, achieving 99% recovery from precipitation tanks.
Flinders University polymer selectively binds gold from solution, enabling solid phase extraction without precipitation.
UV light initiates polymer formation, creating material that chemically bonds with dissolved gold ions. Saturated polymer undergoes pyrolysis at 600 degrees, releasing pure gold and regenerating reusable sorbent. Electrowinning plates pure gold from solution using electric current, achieving 99.5% purity.
Process monitoring ensures consistent 98% gold recovery while minimizing chemical consumption.
Recovered gold powder proceeds to smelting, where high temperature melts metal, separating impurities. Induction furnaces melt gold at 1,064 degrees, while flux chemicals bind impurities into removable slag.
Molten gold reaches 1200 degrees, producing characteristic orange glow and liquid metal consistency.
flux creates slag layer containing copper, iron, and other base metals floating above pure gold.
Careful slag removal requires precision, preventing gold loss while eliminating contamination.
Pure molten gold pours into preheated molds, forming 1 kilogram bars or smaller ingots.
Controlled cooling over 30 minutes prevents cracking while maintaining uniform crystal structure.
Solidified gold bars emerge at 99.5% purity, requiring final electrolytic refining for commercial grade.
Electrolytic refining dissolves impure gold anodes, redepositing 99.99% pure metal on cathodes. Controlled current at 1.5 volts selectively transports gold ions, leaving impurities as anode slime.
Refined gold grows on cathode as dendritic crystals, achieving 4 nines purity, 99.99%. Anode slime holds valuable byproduct metals, silver, palladium, platinum, undergoing separate recovery.
After 72 hours, electrolysis completes, yielding pure gold, ready for final melting and certification. Refined gold remelts for casting standard 1 kilogram, 400 ounce, or custom denomination bars.
Certified pure gold pours at 1100 degrees, producing commercial-grade bullion, meeting LBMA standards.
Slow cooling produces characteristic bright yellow color and reflective surface of pure gold.
Hydraulic stamps imprint bar details, weight, fineness 999.9, refinery mark, and unique serial number.
XRF analysis confirms 99.99% gold, with trace impurities below 100 parts per million.
Traditional fire assay provides definitive purity measurement, serving as quality benchmark.
Complete documentation includes photographs, assay certificates, and blockchain tracking for provenance.
E-waste contains 400 grams silver per ton, recovered through parallel processing streams.
Palladium concentration in electronics averages 20 grams per ton, commanding $30 per gram market price.
Neodymium magnets from hard drives undergo specialized extraction, yielding strategic rare earth metals.
E-waste aluminum from housings and heat sinks melts at 660 degrees for recycling.
Plastic components sort by density and polymer type, creating recyclable feedstock.
Glass fibers from PCBs combine with CRT glass, producing construction aggregate. Advanced treatment removes heavy metals and neutralizes acids, achieving zero discharge standards.
Ion exchange resins capture trace precious metals, preventing environmental release and loss. Automated pH control neutralizes effluent to 6.5 to 7.5, meeting discharge regulations. Filter presses dewater treatment sludge, recovering water while concentrating metals for reprocessing. Wet scrubbers remove particulates and acid gases, achieving 99.9% emission control.
Carbon filtration captures organic vapors and dioxins, preventing atmospheric release. Hazardous residues store in sealed containers, awaiting licensed disposal or specialized treatment. Waste heat from furnaces preheats incoming materials, reducing energy consumption 30%. Rooftop solar arrays generate 20% facility electricity, supporting sustainable operations.
Daily testing verifies air emissions, water quality, and soil protection, meeting regulatory standards.
Mandatory safety training and protective equipment prevent exposure to chemical and metal hazards.
Computer systems log all environmental parameters, providing regulatory agencies real-time compliance data.
Processing 10 kilograms PCBs costs $72, producing 1.4 grams gold worth $6,260 at current prices. Urban mining gold costs $1,455 per ounce versus traditional mining $1,800, including environmental compliance. World e-waste contains $50 billion uncaptured precious metals, growing 5% annually.
Only 17.4% global e-waste reaches formal recycling, while 82.6% enters landfills or informal sector.
Annual smartphone sales represent 47 tons of gold, requiring extraction from 100,000 tons of ore traditionally.
Urban mining produces 85% less CO2 than traditional gold mining, eliminating 52 million tons emissions. E-waste recycling uses 90% less water than mining, eliminating toxic tailings contaminating groundwater. Urban mining eliminates habitat destruction, deforestation, and community displacement from traditional extraction.
Circular economy principles keep valuable materials circulating and reducing virgin resource dependence.
Domestic urban mining reduces geopolitical metal supply risks, providing national resource security. Formal e-waste recycling employs 50,000 workers in high-skill manufacturing and technical positions. Continuous innovation drives efficiency improvements, targeting 99.5% precious metal recovery by 2030. Venture capital investment in e-waste technology exceeded $500 million in 2025, supporting scalability.
Extended producer responsibility laws require manufacturers fund e-waste collection and recycling infrastructure.
Manufacturer take-back programs collect 40 million devices annually, supporting responsible recycling. Public education campaigns increase e-waste recycling participation rates from 20 to 35%.
Basel Convention regulates transboundary e-waste movement, preventing illegal dumping in developing nations.
Safe gold extraction technology transfers to small-scale miners, eliminating mercury use, protecting health.
E-waste generation projected to reach 74 million tons by 2030, requiring urgent infrastructure expansion.
R2 and e-Steward certification verify responsible recycling practices, protecting environment and workers.
Urban mining operations span 50 countries, with largest facilities in China, Japan, Switzerland, and Germany.
Tokyo 2020 Olympics produced 5,000 medals from 6 million recycled phones, demonstrating urban mining viability.
Switzerland achieves 95% e-waste collection through comprehensive producer responsibility and consumer participation.
Chinese research achieved world's highest, 98.2% gold recovery, using room temperature chlorination process.
Mint Innovations bacterial extraction commercializes, achieving economic viability in 2025 Sydney facility.
Britain's 1,100-year-old Royal Mint employs cutting-edge chemistry, extracting gold in minutes, not hours.
Australian green chemistry enables polymer recycling and gold recovery, simultaneously advancing sustainability.
India's largest e-waste processor, Atero, extracts 3,000 tons precious metals annually from 120,000 tons waste.
Formalization programs in Ghana and Nigeria improve worker safety while capturing economic value.
Blockchain technology verifies ethical sourcing, eliminating conflict metals from electronic supply chains.
AI-powered vision systems identify components with 99.5% accuracy, improving recovery efficiency.
Container-based processing units deploy in cities, reducing transportation costs and expanding accessibility.
Major manufacturers commit using 50% recycled metals by 2030, driving urban mining demand.
Next-generation recovery targets lithium, cobalt, and rare earths, supporting battery and magnet production.
Scalable technology allows community-level recycling, bringing economic benefits to local populations.
Technical training programs prepare workforce for growing urban mining sector, requiring specialized skills.
International cooperation strengthens regulations ensuring safe, profitable, and environmentally sound recycling.
From discarded electronics to certified gold bars in 72 hours, proving urban mining's commercial viability. E-waste urban mining proves yesterday's trash becomes tomorrow's treasure through innovation, technology, and sustainability.